We're going to do the classic shadow problem here. It's a common related grades problem, and you might think of it as the lamp post problem. So you have a guy that's walking away from a lamp at a particular rate. So in this problem I said that the lamp is 20 feet tall. The guy is 6 feet tall. Presumably they're both perpendicular to the ground. And he's going to walk away from the lamp at 5 feet per second. And then there's two questions that you typically have to answer. The first one is, at what rate is the length of his shadow? So I'm kind of color coding this so you can look at the diagram and see his shadow in the diagram. So the shadow's y in this case, growing when he is 8 feet from the lamp. And then the second question is, at what rate is the tip of his shadow? And sometimes it says moving across the ground, moving away from the lamp. There's a bunch of options there. But that's actually a different question. I think the conceptual problem is some people think that's the same exact question, but it's really not. And so let's tackle the first question. So that's going to be the rate at which the length of the shadow is increasing when he is 8 feet from the lamp. It turns out the answer is going to be independent of the distance, which has always weirded me out. So let me just recopy my figure here. So I got the lamp, I got the guy, calling that x, calling that y. So x is how far he is from the lamp, and then y is how long his shadow is. And x is going to be 8 feet. dx dt is going to be 5 feet per second. That's given. And what we're looking for is, well, we know y is the length of his shadow, and we're trying to find dy dt. So what we're going to do here is set up some similar triangles. This problem really just comes down to using similar triangles. And in this particular case, what I'm going to do is the largest right triangle that you see, and then the smaller right triangle that involves 6 and y. So let's set that up. So we get 6 over 20, so that's the, the height of the smaller triangle over the height of the larger triangle. And that's going to be equal to y, which is the base of the smaller triangle, over x plus y, which is the base of the entire triangle. Now we're going to algebra. So cross multiply, and then distribute, and then bring everything to one side. And then I'm going to solve for y because I want to find dy dt. And now I'm going to take the derivative of both sides with respect to t. So dy dt is 3/7 of dx dt. I'm told in the problem that dx dt is 5. And also notice that this derivative has nothing to do with the actual current value of x, which is why it's independent of that. So dy dt works out to 3/7 of 5, which is 15/7 feet per second. Alright, so that's one way to solve this, but I'm going to show you another way. And so let's say we do this problem again. And I'm going to add some stuff. So what I'm going to add is a line parallel to the base, kind of off of the guy's head. So right there. So that's obviously going to have a length, so it's perpendicular, so I put those in. But it's going to have a length of x feet, because you have a rectangle there. And also, since the guy is 6 feet tall, that segment there is 6, and you can see that my drawing is to some sort of wonderful scale. But more importantly, that little segment there, the top part that's left of the lamp, must be 14 feet, because 14 plus 6 is 20, in case you couldn't work that out. And now, actually, do you see the two similar triangles that are small? So there's the one where the guy is the height, and then y is the base, and the other where 14 is the height and x is the base. Those are similar triangles by angle, if you want to get into that. But suffice it to say they're similar, which means we can actually set up this ratio. Y over 6, so the base over the height, should be equal to the other base over the other height. Can cross multiply. So this is just faster. And every year I have like one student who figures this out, and every summer I totally forget about it. And every year I'm just amazed that this works. But either way, that gets you the answer really quickly. So you might want to consider that method, but it does require a little bit of ingenuity, I guess, to kind of see that and be like, oh yeah, I'm going to do that. Alright, let's take a look at part B. So, redrawing the figure. Doing a lot of that here. Alright, so remember B, we're looking for the rate at which the tip of the shadow is moving across the ground, or how fast it's, I don't know, getting away from the lamppost. So the whole shadow is, not the whole shadow, sorry. The distance from the base of the lamp to the tip of the shadow is x plus y. So that's actually the location of the tip of the shadow always relative to the lamp would be x plus y feet away. So what we're looking for is we're looking for the derivative with respect to time of x plus y, which is that entire distance. And we know that that's just going to be dx dt plus dy dt. And this is why this is part B instead of part A, because we're going to use the answer to part A. So we're given that dx dt is 5. We calculated dy dt was 15/7. So overall we get 50 over 7 feet per second. And that's the shadow problem. So I hope you found this helpful, and good luck.